Alright, so now that we have the equation from the Rachford-Rice method, we can go ahead and solve a problem involving a flash calculation. So over here, we will be solving problem number 4 here. It is a fixed temperature and pressure flash calculation with a feed of 4 moles benzene and 6 moles of toluene. The flash drum is set at 393 Kelvin and 150,000 pascals. So I'm going to go into Collaboratory and define these. So our temperature is 393 Kelvin. Our pressure is 150,000 Pascal. And then our feed in has 0.4 moles of, or 4 moles of toluene and, or 4 moles of benzene and 4 moles of, or 6 moles of toluene. So the mole fraction is 0.4 benzene and 0.6 toluene. And then we can also define F, which is our feed in, as 10 moles per second. Since we have 4 moles of benzene per second and 6 moles of toluene per second, the total is just going to be 10. So now I can go ahead and code in our equation that we need. So in the numerator, we have Z times K minus 1. And then in the denominator, we have 1 plus our vapor mole fraction, which is this V over F value here. I'm just going to call it one variable for now, kind of makes the calculation easier, times K minus 1. So before I go ahead and do this, I'm going to define K, which in the last part of the video, we saw that it was the pure component saturation vapor pressure over the total pressure. So that is just going to be P dot P vap at our specified temperature over the total pressure. So now we have this summation notation in front of our expression. So we have to add up all of our mole fractions, or all of the quantities for each of the mole fractions, each component. And there we go. Now we have our expression, and we need this to be equal to 0. So we have to iterate the value for the vapor mole fraction until it's equal to 0. So how we're going to do that is we're going to use the root function. So I'm going to define a function for our Rachford-Rice. Since we are using it in the root solver, we need to pass a vector to it, and in the vector it's just going to be our unknown, which is the vapor mole fraction. So I'm going to unpack that, and then all we have to do is return this equation as an array. So now we can solve it using root. We have our function, which is RR, and I'm going to make a guess of 0.5. And there is the vapor mole fraction. Yeah, there's the vapor mole fraction. So as you can see, it's over 1, which I'll explain a little later in the video once we get the rest of the parts that the problem's looking for. So it's also looking for the compositions and flow rate of the outgoing vapor and liquid phases. So we need to find the total amount of moles in the vapor phase, the total amount of moles in the liquid phase, and the composition of both of those. So we can find the total amount of moles in the vapor phase using our vapor mole ratio, which we get from our root equation. And I'm just going to grab the first element, or the first index of the x element. That way we just get this value. And this is to get the moles of the total moles in the vapor phase will just be our mole fraction times the total feed, which we defined up here as 10 moles per second. Then to get the total moles in the liquid phase, it's just our total moles going in of the feed subtracted from the total moles in the vapor phase. And then to get our x is to get the liquid mole fractions, we'll use this expression from the last video, which is our mole fractions divided by 1 plus the vapor mole ratio, or the vapor mole fraction, times k minus 1. And then we can get our liquid mole ratio, or liquid mole fractions, using k times x. So now that I have all these values calculated, I'm just going to go ahead and print them out using print statements. So this first one will be our total liquid in moles and then I will do another statement for our total vapor in moles, which is our V variable. And then I can display the liquid mole fractions, which is stored in our x variable, and then the vapor mole fractions, which is stored in our y value, or our y variable. And then I'm actually going to add another print statement right here up at the top to print out the vapor mole ratio, which is just the VF variable that we calculated. So now we can take a look at all these values, and as you can see, our total moles of liquid is a negative value, and our vapor mole ratio is greater than 1. It's actually about 2.5. And the reason for this is because for our flash calculation, we did it at a set temperature of 393 Kelvin and a set pressure of 150,000 pascals. And if you come and look at our dew and bubble pressure graph, you can see that we are outside of the two-phase envelope here. So since our pressure is lower than, our pressure is below this line, we will have all vapor in this calculation, and really no flash reaction is going to happen. Your feed is just going to stay all in the vapor phase. If we were to increase the pressure so that we are inside of our two-phase envelope, such as raising it up to 180,000 pascals, and then we redo our calculation, you can see we get meaningful values. So the mole ratio is less than 1, and we have positive values for both the total liquid moles and the total vapor moles. But this problem specified 150,000 pascals, so I'm going to change that back and display the answers just one more time.